We have been detailing about the periodic classification. What we will do today is, if you want the detailed explanation, I think you can go ahead and check out what are all the subtopics we have discussed in very detailed manner, right? If you wanted to know the concept in detail. Now, suppose if you're writing your exam is hanging on your head, and we wanted to do it very quickly as a single page document, right? Let us consolidate this chapter and write all important things at one place. Well, I would like to brief the entire chapter, right? And what are important, I would like to underline. So the students who wanted to have a quick revision can actually go through this session where I'll be consolidating the entire chapter of periodic classification and then venture into the new chapter. I'd love to tell you, always when we discuss periodic classification, one thing is important, right? Each period is a shell. Remember that. Each period is a shell, and remember that shells are infinite in an atom. And they are designated by principal quantum number. And the principal quantum number varies from n is equal to 1 to n is equal to infinity, right? So when you have infinite number of shells, you can actually expect infinite number of what? Periods. But if you look into this, you have around 7 periods, and the 7th period itself is incomplete. And when the 7th period itself is incomplete, it leaves the scopes for you to go out, check out any new elements hiding in one another, or you can mine it out or dig out the entire surface, right? From many years from now, I think you have the position of that element in the periodic table fixed. You must understand. That is one of the biggest features of what? The periodic table. People who have, limited knowledge, what they think is, the periodic table is silly, trivial, where I have been given some elements and asked to place them in rows and columns, and I've taken a pen and scale and done it. No, absolutely not. Absolutely not. In fact, I would like to say it stimulates research. It rather stimulates research. It's not such trivial. It is driven by principles. It is driven by rules. And there are schemes of distributions of electrons. Absolutely nothing is random in chemistry. Understand that. Absolutely nothing is random in chemistry. Everything is ordered, right? And they are driven by rules, principles, and schemes, right? So if I can put all these at one place, what are the important points? Then I would like to start off from here. Watch carefully here. This is a single page document, and this document is just enough for you to write the exam very quickly when it is actually, you have a short period of time. If you want complete details, I think every topic has been detailed in a very, very, very detailed fashion. You can go through it and learn the concept. But right for now, I think I'm writing all the important points at one place. Here is the first point. Watch carefully here. So each period is basically regarded as a shell. Each period, what you see, is regarded as what? Shell. If it is regarded as shell, then shells are designated by principal quantum numbers, PQNs, where n values will be starting from 1, 2, 3 and goes on to infinity. So it clearly indicates that when shell is a period, you can expect infinite number of what? Periods. But if you actually see the long form of periodic table, you will actually see that the periods are only 7 and the 7th period itself is incomplete. So you have 8th, 9th, 10th, 11th, and you have the scope. You have a lot of scope for you yourself itself. I think you check out some more elements which are left outside, which we have not yet discovered. Right? So you understand that each period is regarded as a shell, and shells are designated by what? Principal quantum numbers. You must understand. The second thing, what is important is modern periodic table will be having 7 periods, right? And 18 groups. You must understand. They have 7 periods and 18 groups, and the 7th period itself is what? Incomplete. And also I would like to say that there is a modern periodic law which governs the mode of activity of all these elements that are in the periodic table. Now, mode of activity is what? Mode of activity is nothing but the physical and chemical properties exhibited by all these 120 odd elements that are discovered till date. Metals and non-metals, they have some certain specific properties, physical and chemical, which I call it to be mode of activity. right? They are all governed by a periodic law. Well, I would like to write the law for you. So please understand that this modern periodic law, right? The mode of activity of elements, right? Basically, they are functions of atomic radii, right? You must understand, I was always telling in the entire, when I was detailing the entire chapter, I was always telling that you name any periodic property which repeats itself at regular intervals, they're all functions of atomic radii. So if you ask me, like you have 120 elements in the periodic table, and what is the difference between all the 120 elements in the periodic table? It's basically size. So the mode of activity which I'm referring to is nothing but the physical and chemical properties, and they are all functions of what? Atomic radii, you must understand. If you're small, you will actually exhibit certain mode of activity. If you're bigger, then you exhibit different what? Physical and chemical properties. If you're moderate in size, you have a different what? You exhibit what? Different what? Properties. You must understand that. Right? So, mode of activity is nothing but physical and chemical properties are functions of what? Atomic radii, you must understand. So, the most critical part is atomic radii. Well, if you recollect, I was basically telling that atomic radii, if you look into the definition, I'm not going to write the definition again, but remember that atomic radii is nothing but the distance from the nucleus to the outermost shell. Nucleus to the outermost shell. Well, it looks simple, but when you wanted to apply it practically, then you have some practical problems. Like, for example, nucleus to the outermost shell. Outermost shell is not a laid down cement road which is around the nucleus. You must understand. If you have an electron, you have a shell. If you don't have an electron, you don't have a shell. You must understand. So there is a shell itself is what? Electron. No electrons, no shell. So if someone is telling me that it is the distance from the nucleus to the outermost shell, and outermost shell is nothing but the electron, but Heisenberg says that you cannot actually determine the exact position of an electron or the velocity of an electron. So you telling me from the nucleus to the outermost shell seem to be absolutely ideal, and it's not applicable. It's fine that you can actually put it on a frame and hang it out in your room, but it's absolutely ideal in nature, because first of all, isolating the atom itself is difficult. You isolate an atom and cut it with a knife and then open it, take a pencil and a scale, and then from the nucleus to the outermost shell. And if at all you do it also in the outermost shell, the electron's position is not fixed. There's a lot of uncertainty in it, says Heisenberg. So in such scenario, you telling me this definition is absolutely ideal and we don't consider it for any operational purposes. So what we do, we didn't run away at that point of time, but I think what we have done is actually proposed 4 operational definitions for it. Remember that when for the atomic radii, right, you actually mentioned 4 operational definitions. 4 operational definitions. Why 4? Because if you look into the basis of me proposing to you 4 operational definitions for 1 atomic radii definition, which is absolutely ideal, the basis is basically the nature of bonding. And remember that in chemistry you don't have one bonding. You have covalent bonding, you have ionic bonding, you have no bonding at all, and you have metallic bonds also. So if you have one bonding, that's fine, but you have different types of what? Bonds. So I think I propose alternately 4 operational definitions for atomic radii, because measuring atomic radii is ridiculous by going by the definition, because it's asking us to isolate an atom, get a knife from the kitchen and cut it off and open it off and take a pen and scale from the nucleus to the outermost orbit, and then you measure it off. It's absolutely not possible, right, with 1 atom. So we take 2 atoms and we ensure that the 2 atoms are very close to one another, and the atoms are very close to one another once they are actually in a bonding mode. And when they're participating in bonding, it's no one bond, you have 4 types of bonds. So I propose 4 types of definitions, right? And the first one is covalent radii. It's basically covalent radii, and this is nothing but covalent radii is nothing but bond length by 2. This might be a question in exam. The covalent radii is basically bond length by 2, right? So when two atoms approach each other, for bonding, initially they're excited, so they're moving towards one another, losing energy. losing energy. So the potential energy is actually what? Decreasing. But at some point of time, you get your electronic repulsions. So then suddenly after a certain point, they stop because the potential energy graph grows up and it's, it's exponentially, it is increasing. So at some point of time, they stop at a distance, and that distance can be called as what? Bond length. And bond length by 2 is nothing but what? The covalent radii. That might be a question, right? And the second one is van der Waals radius. And the second one is van der Waals radius. And this is mostly for people who don't participate in bonding. That's noble gases, right? Never apply van der Waals radius for covalent radius, because this is applicable, this covalent radii, people apply it for people who participate in bonding, like this. Chlorine, chlorine. This is most applicable to the single bonds, hydrogen, hydrogen, chlorine, chlorine, where that is the bond length, and you divide it by 2, you get what? The covalent radius. So the bond between two nonmetals is essentially covalent. So you take all the nonmetals when they are participating in bonding, it will essentially be covalent bond. They stop at a distance, that is called bond length, and divide it by 2, it's nothing but covalent radii. Right? That's one point. And coming to the van der Waals radius, it's applicable for noble gases. What happens in noble gases is they don't participate in bonding under normal conditions. Yes, they do at drastic conditions, but I think at normal conditions they are not actually participating in bonding. So what you are supposed to do is you need to induce a force. Normally they don't attract, right? So what you do is you apply pressure onto two gaseous noble gases, noble gas atoms. You bring them together, right? Apply pressure, chill them, chill and apply pressure together sometimes, yes. Yes, chill and apply pressure, they are together now, and when they are together, the equilibrium between the positive and the negative charge gets disturbed. So you have a van der Waals force, and then the van der Waals force, once it is existing, you're supposed to take the distance between two adjacent atoms and make it a half, then you get van der Waals radius. Well, the details have been already told to you. The only important thing what I would like to tell is van der Waals radius is applicable for what? Noble gases. If someone is applying van der Waals radius to hydrogen, it is not prudent, it's not wise, it's actually stupidity. It's idiotic rather. Why do you want to apply van der Waals radius to hydrogen? If you wanted to, you can. Just to check it out whether van der Waals radius is bigger or smaller for your own information. But it is ridiculous to apply what? Van der Waals radius to hydrogen, because hydrogen is participating in covalent bonding. That is a better way, that is a prudent way to understand. Then if that is the case, this is applicable for noble gases, and you should understand this is a question. In fact, van der Waals radius is greater than what? Covalent radius. In fact, greater, it's almost 1/3 greater, it's almost 30%, 28 to 30% more than covalent radii. So why would anyone wanted to choose van der Waals radius for covalent radius? Better stick to what? Covalent radius, because van der Waals radius is greater than what? Covalent radius, and this is only applicable for people who do not participate in bonding. Why do you want to apply it for hydrogen? And already we are running error. Instead of taking one atom, when you take two atoms, you're actually inducing error. To reduce the error, I think we should actually ensure that the atoms participate in bonding. That is the situation. So in van der Waals radius, they are not participating in bonding. You are actually inducing a van der Waals force, which is a weaker force than covalent force. So it is not advisable for you to actually take van der Waals radius for what? Hydrogen, chlorine, when you have covalent radii. That's important. For details, you wanted to do it, I think I told you detailedly. This is van der Waals radius, and then coming to metallic radius. This is metallic radius. I think you have minimum error here. Minimum error here, because what happens in metals is, in metals, the atoms are supposed to touch each other. Well, naturally, when the atoms are supposed to touch each other, then I think you just take the internuclear distance and make it half. That straight away gives you what? The metallic radii without any nonsense. Right, we need not induce anything or something like that. So I think the minimal error what we get it is inward metallic radius. It's almost accurate, right? And remember that's metallic radii used for what? Metals where you have what? Metallic bonds, right? That's one case. And finally you have ionic radius, and for ionic radius, this is for radicals, that is positive ions and what? Negative ions, the cations and the anions. And for them we use the ionic radii like zirconium +4 and hafnium +4. you have, similar radii, 83 picometers and 84 picometers, right? That's an ionic radii, right? And I was telling you something about ionic radii, which I would like to write. So before I rub this slide, understand that each period is regarded as a shell. Shells are principal quantum numbers. Modern periodic table has this many periods and 18 groups. The mode of activity, that's nothing but the physical and chemical properties. They are all functions of atomic radii. And atomic radii being purely idealistic, I prefer having an operational definitions for all this. And here are some of the important points. Don't apply van der Waals radius for hydrogen and chlorine, because you end up with error, because already you're living with what? Error. We must be minimizing it, right? That's one case. Going ahead, here is a few points, some more points which are important. Watch carefully here. And as far as ionic radii is concerned, I think what you do for ionic radii, right, what you do is use Z by E. Use Z by E. This is nothing but the total positive charge divided by the total negative charge. So the total positive charge distributed among all the electrons in a species can be called as average force of attraction. So the Z by E is nothing but average what? Force of attraction. You must understand. This is average force of attraction. And you must understand Z by E is inversely related to the size. So if the Z by E is more, the size is less. After all, the average force of attraction is more. The outermost shell is pulled inwards. So the size basically what? Decreases. So if I can give you an example for this, I told you it is aluminium plus 3, aluminium plus 1 rather, and aluminium plus 2, and aluminium plus 3. If you look at the Z here, it is 13, it will remain 13, it will remain 13, it will remain 13. But if you see the number of electrons, it remains 13, but it is actually 12 here, it is 11 here, it is 10 here. Now if you actually find out Z by E, this is 1, and this is greater than 1, this is greater than 1, and this is greater than 1. You must understand. So Z by E is inversely related to size. So if you write the size trend, it is aluminium, which is greater than Al plus, which is greater than Al plus 2, which is greater than Al plus 3. You must understand. So the least size is possessed by what? Aluminium, and the moment you remove one electron from an element, it forms a cation, and thereby the size goes on shrinking if you further remove the electrons or extricate the electrons from an element. You must understand that, right? So that is how so if someone in the exam, suppose if he is giving you several cations for you, and then asking you to find out the size trend, then I think one must use Z by E. Z by E is nothing but the average force of attraction that exists in an ion. You must understand Z by E. You must understand that, right? So if that is the case, then Z by E is more, the size would be what? Lesser. I think it's a common sense. Average force of attraction, when it is more, the size would be what? Less. You must understand that, right? So that is one point which I wanted to say. Use this when you wanted to judge ionic radii, which is normally given in the exam, right? That's one point. The next point, observe carefully. Here is the important points here. Ionization potential, or I call this to be ionization energy, right? Ionization energy, you must understand. Now ionization energy again is inversely related to size. So ionization energy, IE, is inversely related to the size. So you must understand, smaller the size, greater is what? The ionization energy. But what is it? What is that in this? It's important for the exam. What are the questions given in this? Well, I was telling you that, he will give you 4 ionization potential values, 4 IP values, I1 for an element, 4 IP values for an element. Right? For a particular element, say M. He will give you 4 ionization potential values and ask you the formula of chloride, the formula of oxide, the formula of nitride, or anything, formula of fluoride, chloride, or bromide, or nitride, or oxide, whatever you should be in a position to tell. So the formula unit of a particular element M can be judged on the basis of ionization potential values is a typical question in the exam. Is a typical question in the exam. For example, if I can illustrate very quickly for you, for an element M, I1 is 10 electron volts, I2 is 26 electron volts, I3 is 86 electron volts, and I4 seems to be 500 electron volts. So he has given 4 IP values. Now he is basically asking me, formula of 1 chloride. He's asking the formula of oxide. He's asking the formula of nitride. Right? You must understand. He's asking chloride formula, oxide formula, and what? Nitride formula. Right? We should be in a position to judge these formulas on basis of what? Ionization potential. This is an application for people who are actually writing their JEE exams or a NEET exam. This is a typical question. No one will ask you the definition of ionization potential. That's only for your conceptual purpose, which I detailed when I was lecturing the periodic classification, right? So what are the applications of ionization potential? Is simply he'll give you 4 ionization potential values of an element, and he will ask you to find out the chloride formula, oxide formula, and what? Nitride formula. How do we do that? Look into this. The first ionization potential is 10 electron volts. That means the energy supplied to extricate the first electron in the outermost shell is 10 electron volts. He spent 10 electron volts. He has spent basically what? 10 electron volts. And I'm not surprised. You need to give some energy to kick an electron out because the electron is held by the nucleus with great force, right? 10 electron volts. And the second one is 26, which is even not surprising for me, because when you remove one electron, the atom size shrinks. The atom size is what? Shrinking. And if you remove further one more electron, the atom size further shrinks, right? So I think as the positive charge is increasing, the size is actually what? Decreasing. It would be increasingly difficult for you to remove the electrons. So naturally, this is I1, I2 and I3. So naturally you can expect I3 is greater than what? I2 is greater than what? I1. In fact, I3 is greater than what? I2, which is greater than what? I1, which is no surprise, right? The ionization potential goes on increasing. So these three seem to be absolutely normal values. These three values seem to be absolutely normal. But the fourth one seemed to be an extraordinary one, and it's a bigger jump. Look into this, is 86. It's 10, 26 and 86 seem to be okay, but 86 to 500 seem to be a bigger jump. Now what has happened here is basically, if you give a schematic representation, here is where the outermost shell, and you have 3 electrons here, and here you have 1 electron. You assume that you have 3 electrons over there, and the first one was taking 10 electron volts, the second one was taking 26, and the third one was taking 86, and the shell vanished now. It has only 3 electrons, the shell got vanished. No electrons, no shell. Now we are actually coming close to the second shell, which is much closer to the nucleus, right? So there is no shell. The third shell has only 3 electrons, right? So the shell vanished when the electrons have vanished. Now you are much closer to the second shell, and it is extremely difficult for you to remove this electron, and extremely difficult. That is actually viewed as a abnormal value, or I call this to be a jump, right? And even a graphical representation would tell you, if this is ionization energies, the first ionization energy is I1 here, and the second one also is I2 here, and the third one is also what? I3. These three are normal. But coming to the I4, there seemed to be an absolute jump. The huge jump between I3 and I4, indicating that we have actually entered into a new shell, and the outermost shell disappeared. The outermost shell basically what? Disappeared. If this is the case, and if the outermost shell gets disappeared, then you will spend more energy. So ultimately what I mean to say for people who are preparing for the exam, for them you must understand number of normal values. I write it here. Number of normal values is nothing but the number of valence electrons. That means the number of electrons that are present in the outermost shell. Number of what? Normal values is nothing but the number of what? Valence electrons that are present in the outermost shell. Then I think that number of valence electrons is nothing but group number. That's nothing but group number. So total number of electrons that are present in the outermost shell of an atom is nothing but the group number. So carbon has 4 electrons, so it's 4th group. Nitrogen and phosphorus have 5 electrons, it is 5th group. Oxygen and sulfur has 6 electrons, so it is 6th group. So the number of valence electrons present in the outermost shell is nothing but what? The group number, and there is group number, so the number of normal values are 10 is fine, 26 is fine, 86 is fine. This is not, this is a huge jump. This seems to be an abnormal value. So now here in this case, the number of normal values are 3, valence electrons are 3, so the group number is 3, and if the group number is 3, an element in group 3, if you can see, it's nothing but aluminium, so the aluminium chloride formula will be AlCl3, and it is Al2O3, and then find Aln. So in case of M, I think it is MCl3, it is M2O3 and Mn. These are the answers you must understand, and the fourth values seem to be abnormal, so you need to consider only normal values, and the number of normal values are nothing but what? The number of valence electrons, and the number of valence electrons is nothing but the group number. You must understand that is one question which he will be asking in exam. That is one question he will be asking in exam, you must understand. And coming to the third important point, observe carefully here, important, and remember that shielding effect, right? The shielding effect actually is one of the factors which influences what? Ionization potential. And it has its own application. Each application is a question in exam. Each application is a question in exam which we would like to discuss. Remember what is shielding effect? If in between the nucleus and the outermost shell, if someone is asking what is shielding effect, then you tell them that in between a nucleus and the outermost shell, if the number of shells increase, if in between a nucleus and the outermost shell, if the number of shells goes on increasing, then the nuclear force of attraction that is supposed to be falling on the outermost shell basically decreases. So there is the effective nuclear force of attraction. Let me use that word effective. Effective is nothing but resultant. So if you can explain properly that from the nucleus, in between nucleus and the outermost shell, if the number of shells increase, then the resultant nuclear force of attraction that falls on the outermost shell decreases. Then the outermost shell basically relaxes. Relaxing means it is not held by the nucleus the way it should be. In such a scenario, it would be easy for you to kick the electron out. It's easy for you to remove the electron. Easy in the sense you spend less energy. So you actually space energy means the ionization potential would be what? Lesser. So remember, ionization energy is inversely proportional to the shielding effect. So that means more the shielding, more the number of shells, then ionization energy would be what? Lesser. Right? At the same time, even if you look into the shielding power, then S is better shielder compared to P, compared to B, compared to F. S is a better shielder. Now, two things matter in shielding effect. Listen to me carefully. So if in between the nucleus and the outermost shell, number of shells increase, that is one point. But also we need to consider the electrons are in which subshell, because the subshells are also a part of a shell. Right? So it's not a single statement, we need to be more specific. It is like this: if in between the nucleus and the outermost shell, the number of shells increase, at the same time we need to consider the electrons are in which subshell also, that is SPDF. And if you're considering them, I think S is a better shielder compared to P, compared to D, compared to F. There are reasons for that. The S subshell is basically symmetric around the nucleus, it is non-directional. The electron density is basically symmetric along the what? The nucleus, and it is no direction. It has no direction at all. But if you look into the PDFs, the P is directional, the D is directional, and F has its own issues. You must understand. So if you look into the hierarchy in which the shielding is being done, I think the S orbital is a better shielder compared to B, compared to D, compared to F. And the F actually has a different problems, completely different problems. And F, the shape, S orbital shape is spherical. P is dumbbell, D is double dumbbell. F is what? We don't know. If someone is asking you what is the shape of f orbital, actually we do not know. Yes. So now, if this is shielding effect, two things we need to consider. One, how many shells are there in between the nucleus and the outermost shell? Second, where are the electrons placed in the subshells? S, P, D, F, because this is how the shielding effect is, right? And these are not asked in exam. Now, what are asked in exam are two applications. One is a theoretical question. The other is about lanthanide contraction, which is also a direct effect of what? The shielding effect. Both we would like to write all the important points. Watch carefully here. Right, if I can write some points for you as an application of shielding effect. Applications of shielding effect. Then the very first application what I'm writing is this, right? In groups, size basically increases. But the way it increases at the top, not seen at the bottom. Not seen at the bottom. And the reason for that is, of course, what? Shielding effect. And of course, what? Shielding effect. Let me explain this point. When you take any group, all the 18 groups if you take, from top to bottom if you go, the size increase will be observed from top to bottom. That is a proven fact, right? The size will be increasing. But the way it increases, if you can closely observe, the way it increases for the first three elements is completely different the way it increases from the last three elements. Right? So that's why in any group, the first three elements have similar properties and the last three elements have a similar properties. Right? So for example, arbitrarily, if you want me to explain, then it is something like this. If you take the first group, it is lithium, sodium, potassium, you have rubidium and cesium. The size basically increases. The size increases. There is no dispute in that. The size increases in a group. It's a fact. But the issue is, if you look into some arbitrary values, these are not real values. These are not real values. These are absolutely arbitrary for our understanding. Suppose if this is the size of this is 1 angstrom, and the sodium becomes 6 angstroms, and then the potassium is becoming 11 angstroms, and from rubidium it becomes 11.12 angstroms, and then it becomes 11.13 angstroms. Come on. Look at the values. Look at the values. The size is increasing from 1 to 11.13. There is no dispute in that. But look at the way it has increased. 1 to 6 is a jump. 6 to 11 is further jump. 11 to 11.12 is a small, minuscule increase. Small increase. You must understand. And from here to here, it is further small 0.01 increase. So if you look into this, we wanted to know why. We wanted to know why. So two things should be clear. And that's what I've written. In groups, the size increases. But the way it increases at the top is not seen at the bottom. And the reason for that is shielding effect. Now, what is the shielding effect? Look into this. Here, for lithium, sodium, and potassium, the bulk of the electrons, that is between the nucleus and the outermost shell, in between you have shells and subshells, and in between these fellows are occupying S and P. S and P. So for lithium, sodium, and potassium, between the nucleus and the outermost shell, most of the electrons are occupying S and P subshells. And S and P subshells are what? Are very good shielders. Are very, very good shielders. So when they are good shielders, that's why there is a size increase. You can actually see 1 to 6 and 6 to 11. But if you go down the group, the electrons are entering D and F. Electrons are entering D and F, and I was telling you that D and F are poor shielders. When they are poor shielders and most of the electrons are occupying D and F, they are unable to shield the nuclear force of attraction. So the outermost shell is slightly pulled inwards, thereby the way it increases at the top, is not seen at the bottom. You must understand. It's not seen at the bottom. Right? That is the first application. Now, how the question will be asked? Which of the following is true? Which of the following is true? For in a group, size increases then decreases. Is it true? No, absolutely not. Second, in a group, size increases, but the way it increases at the top is not seen at the bottom. That's why the first three elements differ in their properties. Lithium is different from sodium, is different from what? Potassium. The way, the vigorosity, the reactions, the violence which we see in the first three elements is completely different, and compared to what rubidium and cesium, you have a different set of properties because you have almost similar radii at the bottom. You don't have that similarity at the top. So the mode of activity or the properties of elements also differ in a group for the simple reason that's nothing but what? Shielding effect, you must understand. And coming to one more application of shielding effect, the second application of shielding effect, and you get this question, and you will get this question for sure. Application 2 of shielding effect. Application 2 of shielding effect, and I can say the direct consequence of the shielding effect is seen in lanthanides. We actually see this in what? Lanthanides. You must understand that's what we refer to be lanthanide contraction. You must understand, and you will get questions in this. You will get questions in this, you must understand. You will get questions. Whether you're writing your mains exam or advanced exam, there will be questions in this, and I write some highlights of this. Look into this, the lanthanide contraction, some of its properties if you see. 1, contraction in size, watch carefully. Contraction in size is on an average around 0.2 angstroms in lanthanides, that is 57 to 71. This includes lanthanum. Even though technically lanthanum is a D block element based on its electronic configuration, but if you look into the sizes, the average contraction which we find is 0.2 angstrom units, which is not a small one, and it cannot be discounted. You must understand that, right? And then the size basically decreases, and I can simply say density basically increases, and if you look into the hardness, this also increases, and then you have your melting points, this also increases, right? And I continue to write lanthanide contraction, the complex forming tendency, CFT, if I can write it completely for you. The complex forming tendency, that's nothing but the CFT. The complex forming tendency, the CFT, increases. That increases from what? The lanthanum to what? The lutetium. You must understand, it increases. Because as the size decreases, one of the criteria to form complexes is the central metal ion should be smaller. The central metal ion must be smaller. And due to this contraction, lutetium seemed to be the smallest among the lanthanides, so its complex forming tendency would be highest and least would be lanthanum, right? So the complex forming tendency increases, and most common oxidation state is +3. Even +4 is also seen in some elements like Nb and terbium, which will show +4. You must understand, right? So Nb, terbium, and those are some of the elements which will be having +4 oxidation state. You must understand here. So complex forming tendency increases. The common oxidation state is what? +3. And I can also say solvation energies. Solvation energy also increase. You must understand. One of the criteria for having a greater hydration energy or greater solvation energy is basically the size must be what? Smaller. And you have lanthanide contraction in place, so it will be decreasing from lanthanum to what? Lutetium. Naturally the solvation would be higher, solvation energy would be higher, and even lattice energy is actually inversely related to the size. So I can simply say lattice energy of lutetium which is smaller, or lutetium compounds, right, would be greater than the lattice energy of lanthanum compounds. You must understand this, right? You must understand that. As the size decreases, I think lattice energy would be increasing, because lattice energy is inversely related to what? Size. You must understand. And then these are some of the properties of lanthanides. And the most important one which I would like to highlight is basically this. Zirconium and hafnium, they have similar radii. And this is the 5th period element, and this is a 6th period element, corresponding 6th period element. And zirconium and hafnium will be having similar radii. And if you look into zirconium ratio, zirconium plus and hafnium plus 4, it is 83 picometers and 84 picometers. The ratio is almost equal to 1, indicating that zirconium and hafnium will be having what? Similar radii. And when they have similar radii, you can expect zirconium plus 4 and hafnium plus 4 having similar polarizing powers. Similar polarizing powers, you must understand. You can't distinguish the polarizing powers of these two cations towards an anion, and polarization is nothing but the distortion of electron cloud on approach of a cation. And the degree of distortion they both produce towards an anion is same. So the covalent character of these compounds also remains to be same, says Fazen, according to the Fazen's rules, right? So this is an important thing. Whatever is on this board now is a question in your exam, right? Let me read it out once again. Contraction in size is 0.2 angstrom units. 0.2 angstrom units where you cannot discount. It is a significant contraction in what? Lanthanides, right? Size decreases, density increases, hardness increases, melting point increase, complex forming tendencies increase, common oxidation states are +3. You also have +4s like Nb and terbium. These exhibit what? +4. Solvation energies are high. Lattice energies actually would be higher for lutetium and lesser for what? Lanthanum. From left to right, you must understand that, right? And also the zirconium and hafnium have similar polarizing powers because they have similar what? Radii. You must understand that, right? This is one of the questions which you get it. And then come to the next point, observe carefully. And some things with regard to electronegativity. 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 Some things with regard to what? Electronegativity. Let us discuss this. And remember that, first of all, electronegativity is also a function of size. It is a function of size, and electronegativity is inversely related to the size. So the smaller the size, more is electronegativity. And remember that since electronegativity is a tendency, it's basically a tendency. Electronegativity is basically nothing but a relative tendency. Relative tendency of attraction of the electron pair in a bond. So basically it is a relative tendency to attract an electron pair towards itself, can be called as electronegativity, and tendency has absolutely no units. It basically has what? No units at all. So they are assigned numbers, and the highest electronegative element is coming what? Fluorine. And after fluorine is no chlorine. After fluorine it is basically what? Oxygen. And then comes what? Nitrogen. And then comes like this. And each of these electronegative tendencies are assigned numbers by Pauling. You must understand that, right? So it's important to write few things. Since it is a relative tendency, if you consider a bond AB, then the difference in theoretical bond energies and observed bond energies is nothing but polarity, right? So I can simply say E dash bond energy of AB, which is observed, minus the E dash of AB, not E dash, E, it's basically E, right? This is actually what? Theoretical. And the difference between this is called delta, and this delta is called polarity. And according to Pauling equation, XA minus XB is 0.208 into root delta. And in the examination, he will give you theoretical bond energies and observed bond energies, and the difference between these two is nothing but delta. That might be a question, first of all. And the Pauling's equation, if you actually see, the Pauling's equation is XA minus XB is 0.208 into root delta, where XA is electronegativity of A and XB is basically electronegativity of B. You must understand. And the difference between them is nothing but what? 0.208 into root delta, and where root delta is basically nothing but what? Is difference of what? The practical bond energy, observed bond energy, and what? Theoretical bond energy. Because in theoretical, you're discounting the polarity. That is unequal sharing of what? Bond pair. The details have been given in the subtopic. If you wanted to revise that, you can, but at this document, a single page document, then understand that which of the following is a Pauling's equation is a question in exam which I have seen. Right? So the Pauling's equation is XA minus XB. That is the difference in electronegativities in a bond of both the elements, because it's a relative tendency, which is 0.208 into root delta. And the polarity will be also asked in the exam. The polarity is nothing but the difference of observed bond energy and what? The theoretical bond energy, where theory assumes that the shared pair is always at the center. Right? That's one question. Now moving forward, this is another question. Watch carefully here. Coming to electron affinity. This is nothing but, this is energy released. So it's basically exothermic. So the first electron affinity is always what? Exothermic. The second electron affinity is always what? Endothermic. Third will be naturally endothermic. Right? What is electron affinity? It's also a function of size. It's again a function of size. And remember that electron affinity is inversely related to size. Right? But I think one of the questions which he will be asking in exam for you is basically a discrepancy which we notice. The discrepancy which we notice. What is the discrepancy which we are noticing it? Well, observe carefully here. Observe the discrepancy as a question. The discrepancy. Right? The size of fluorine, if you see, the size of the fluorine atom, the size of fluorine is smaller than the size of what? Chlorine. I think you'll agree, because the chlorine is placed below fluorine in the periodic table, so you expect chlorine to be having a much bigger size. If that is the case, then electron affinity is inversely related to size. It's basically inversely related to size. So we expect electron affinity of fluorine greater than what? The electron affinity of chlorine. You must understand, this is the expected one. But if in reality, the electron affinity of what? Fluorine is slightly smaller compared to electron affinity of chlorine, you must understand here. And this is the real trend. That is the reality, and this is the real trend, and we don't expect this. Right? This will be, the reason for this is asked as a question in the exam. Right? If you wanted to write, this is the question which he will be asking. Why electron affinity of fluorine smaller compared to the electron affinity of chlorine? In fact, let me remind you, the chlorine has the highest value of what? Electron affinity in the periodic table. Rather, right? If that is the case, if this is lesser than this, then the answer, simple single word answer is this. This is inner electronic repulsions. You must understand. It's basically inner electronic repulsions, which are actually the value of electron affinity of fluorine is dropping just below, not great drop, understand, not great drop. And in fact, if I can write it for you, this is how they look like. Watch carefully here. If you add fluorine and chlorine, you add one electron. They both love the electrons, and they readily form what? Cl minus. And you have your energy released here, E1 and what? E2. Both are exothermic. Both are exothermic. But the value is just greater. Just greater. 2 or 3 points here and there, it's greater, and the reason for that is inner electronic repulsions. And these are due to small size of fluorine. Small size of fluorine, and I can simply say the p subshell of fluorine is smaller than the p subshell of chlorine. You must understand that. Right? The 2p subshell, I can simply say the 2p subshell is smaller than the 3p subshell of chlorine, resulting in inner electronic repulsion, not inter. It's not inter. It's basically inner electronic repulsions, and thereby the value drops below what fluorine. And this is a theoretical question. Why electron affinity of fluorine falls below chlorine? And one of the options which he will be giving is inner electronic repulsions. And he might ask you the other way around, rather. The inner electronic repulsions in fluorine is because of. You can simply say smaller size of fluorine. In fact, any question with regard to fluorine, it is small size. Any question with regard to fluorine is because of its small size. And in this case, right, because of small size, and again, if you wanted to be more specific, the 2p subshell is smaller than what? 3p subshell. And the subshells will be smaller if the shells are smaller. And the shell spaces are smaller if the atom as a whole is smaller. And fluorine is one of the smallest atoms in the periodic table because it's placed to the extreme right top. Right? So this is one question with regard to electron affinity. And here comes another one. Observe. This is important. This is basically important. The oxidizing power of fluorine is much greater compared to chlorine, even when electron affinity of chlorine is greater than what? Electron affinity of fluorine. You must understand. That's a question which we need to reason. Understand the question first. Understand the question first. What is the question? Because first of all, understand electron affinity is something which is told for nonmetals. So all the examples which we take are of course what? Nonmetals, and fluorine are of course what? Great nonmetals. They are nonmetals. It says the oxidizing power of fluorine is greater than what? Chlorine. So if you are a better nonmetal, you are supposed to be greater oxidizing power. Right? But if you see the electron affinity of chlorine is greater than electron affinity of fluorine, but still the oxidizing power of what? Fluorine is better than chlorine. You must understand, you need to give that reasoning for that. So I was telling you the reason for that, and this question you will get it in exam. The reason for that is basically interelectronic repulsions. Don't get confused. Earlier we were discussing about inner electronic repulsions. Now I'm basically telling about what? Interelectronic repulsions. And that's again in what? In fluorine, and that's again due to what? The small size. So understand oxidizing power depends on what? So if I can write it for you, oxidizing power is a function of bond dissociation energy first, and even oxidizing power is a function of electron affinity. It depends on two factors, because electron affinity, if you see, it is told for atoms, but you don't find fluorine and chlorine atoms in chemistry. You don't find them because they're extremely reactive. So they exist as a diatomic molecule. So your duty is to first break down them into atoms and then try to add the electron, and they will catch it and the energy is released. That's how the electron affinity is defined. So since no fluorine atoms are available, first is first of all dissociate them into atoms. And that's why I say oxidizing power is even the function of what? Bond dissociation energies. Smaller the bond dissociation energy, more will be oxidizing power. So you can actually say oxidizing power is inversely related to the bond dissociation energy, and oxidizing powers are directly proportional to electron affinity. More the electron affinity, more is oxidizing power. Smaller the bond dissociation energy, more is what? Oxidizing power. In the first case, fluorine passes in distinction, and in the second case, fluorine passes just like that, but the overall values, if you actually see, making fluorine a better what? Oxidizing agent. What do you mean by that? If you look into this question is 100% sure in exam. Bond dissociation energies trend. Bond dissociation energy trend in halogens. It is like this. It starts from chlorine. It's very much higher. It starts from chlorine. And then comes bromine. There is nowhere fluorine here. And it is kicked to the third position. And this is almost 58 kilocalories. This is 26 kilocalories. It is a half. It is half that of chlorine. So what fluorine will do? What fluorine will do is basically, since the bond dissociation energy is very, very small, it first easily breaks. It easily breaks. And it takes only 26 kilocalories. When it breaks, it is ready to accept the electrons and forms fluorine, and the energy is released. This is affinity. You must understand, it's ready. Since the bond dissociation energies are very, very small for fluorine, it easily breaks and ready to accept what? Electrons. And remember that the electron affinity values of fluorine and chlorine hardly differ greatly. So almost have same what electron affinities for fluorine and chlorine. But I think fluorine possessing the smaller bond dissociation energy is ready to take the electrons, you must understand. And the trend of bond dissociation energies follows this trend, and fluorine is actually kicked to the third position. And why such a thing happens is because of inner electronic repulsions. Inner electronic, it's not inner, it's not inner, it's inter. It's inter-electronic repulsions. Now what do you mean by that? If you look into the fluorine atom, look into this. What are inter-electronic repulsions? If you see fluorine, this is the fluorine molecule, right? Why the fluorine-fluorine bond breaks easily? That explanation I'm giving you. Now fluorine belongs to 7th group. So it has total 7 electrons, right? 1 it invested here. So we have to account for 2, 2 and 2. So total 7. 2, 2, 4 plus 2, 6 plus 1, 7. Same is the case with this fluorine. And it invested 1. And since fluorine atom is very small, they are very close to one another. They're very close to one another. And when they're very close to one another, you have 3 lone pairs, this pair, this pair, this pair. They are lone pairs, they have freedom, and they approach each other and then create repulsions. And due to that repulsions, right, that is what is called inter-electronic repulsions. These repulsions will have an effect on this bond, and this bond breaks basically easily. So thereby the bond dissociation energy of the fluorine is kicked to the third position, you must understand. Right? So I advise students for details of the periodic classification, you need to go through the entire chapter for understanding the concept. Right? What I've done today is basically a single page document. Right? You will get 1 or 2 questions, not more than that in JEE mains or whatever exam you write. Right? So this is absolutely enough for you, the single page document, where understand that what are important points you need to highlight if you wanted to write the exam, right? Thank you very much.